Okay, so given that the composition is particularly important to the definition of what's a reservoir gas and what's a reservoir oil, and it's not just important for that; it's important for really any calculations that we'll be making in engineering of reservoir production. So the reservoir composition is a very important to how the reservoir is developed, how many wells are needed, whether you're going to do gas injection. Just a lot of things are affected by the so-called PVT behavior, phase behavior of the reservoir fluids, both when they're flowing in the reservoir, as they flow into the production tubing to the surface, and certainly when they're being processed at the surface and they're creating sellable products. And everywhere in the system, the local composition is important to determine how much of each phase, gas and oil, the density of each phase, and the viscosity of each phase. The density and viscosities are always needed for engineering calculations of transport. Transport in the rock, transport in pipe. Viscosity and density are the sacred properties to do really any kind of engineering calculation. They're dependent on the composition of the oil, the composition of the gas, how much gas, how much oil you have. These are all related directly to what is the local composition. So compositions is something we're gonna spend some time on. And this is just a summary of, get rid of this, the summary of what are the compounds in these so-called reservoir, primarily hydrocarbon mixtures. We have the non-hydrocarbons, nitrogen, CO2, H2S, and we'll always have some H2O. I will say that when we do our calculations, we typically do not take into account the effect that the water molecules have on the gas and oil properties, viscosity, density. We basically ignore that the water molecules are there for most calculations. Okay? You don't have to, but in reservoir and production engineering, which is mainly this department, the interaction of the water phase with the reservoir and gas and oil phases is ignored. Okay? Even though there are water molecules in the air, we kind of ignore it. Okay? So you also can have mercury. Sometimes I think it's referred to mercaptants. I don't really, it's not my area, so I think mercaptant is mercury. We can look it up here, either to show that I had a good guess or I don't know my chemistry. Let's see here, come on. There we go. Mercap. Sulfur containing compound having the formula RSH. Okay. Obviously has nothing to do with mercury, so. Okay. Anyway, mercaptan is an item, but there is also mercury, so that's obviously not the same. And we got the hydrocarbons we've talked about: methane, ethane, and propane. This is probably, on the world basis, the most. There's the most amount. On a global basis from our reservoir gas and oil reservoirs around the world. methane, ethane, propane. We've got the isonormal butane is always quantified separately. Isonormal pentane is also quantified separately. When we get the C6 compound in a PVT report, it'll typically be alkanes, 6 carbon number molecules, but not including benzene. Basically, the lab boils off these components in a gas chromatograph, and they order them in the list according to their boiling point. Okay, and so the benzene molecule boils after normal C6, so it's put into the C7. Okay, so the C7 pseudo C7 component. There's actually multiple compounds in the C7. It'd be all compounds boiling between, I think it's normal C7, normal C8. That would include benzene. Again, I'm not quite sure. I could be, I'm pretty sure that's the case. Let's just look up benzene. Boiling point 80 degrees C. Can you guys remember that? Normal heptane. So 98 degrees C. So what I wrote here was wrong. So hexane. .68, yeah. So basically the C7 would be from boiling from normal C6 to normal C7. Okay. Okay. And likewise for the other compounds, so C8 would contain toluene, which has 7 carbon numbers, and so forth. And then finally they stop separating them into carbon numbers, and they just say, well, this is what's left, the heavy stuff. And there might be, on a mass basis, there might be more than 50 mole percent in that. I mean, it depends on the fluid. There might be a considerable amount. And what the C capital N plus could be, it could be C25 plus, 36 plus is a standard today. It depends a little bit lab to lab and also historically. So before 1980, lab reports only gave C7 plus. They didn't separate 7, 8, 9, and 10. In the 80s, Norway was one of the leading reasons why this went up to C10 plus, maybe C12 plus. In the 80s, Statoil got involved. They had PVT labs, as did Norsk Hydro. And then the 90s, and then now pretty much you get C36 plus as the standard, the heaviest component in the analysis. Okay. There's something called, so these are all C6, 7, 8, 9. These are all really mixtures of several hydrocarbons, right? They're not C7. It's a mixture. There's also some other mixtures that are important. And one is wax, and wax is basically, it starts around C20, I think, but it's the normal C20 out to normal, I don't know, it go out very high, 50 and higher, but it's typically the alkane compounds that precipitate out of the oil because of lower temperature. Okay, so they precipitate out, and it's typically the normal paraffins that form wax, and I think it's in the range of 20 to higher molecular weights. And how much the distribution of the C20s versus the heavier depends on the temperature at which it precipitates and the oil it comes from. So, but it's in this range here, I'm pretty sure. You know, Google is terrible. You get addicted because, you know, before I could just tell you that's what it was and you'd believe me. Now you can go somebody's going to go in and find out that wax, you find out that it wasn't that. Somewhere in here it should give. Does it say distribution of components, petroleum waxes? Okay. I'm going to let somebody else out there find out, but I think it's correct. So basically, it's precipitating because of temperature reduction. Okay, so it's not going to precipitate in the reservoir, but it'll precipitate in the production tubing, maybe certainly in the process facilities where the temperatures reduce. Asphaltenes are often huge mixture of really large, monster compounds that can have molecular weights that are greater than 1,000. Maybe, there are a lot of cyclic aromatic compounds included. They're really nasty stuff. And asphaltenes, when they precipitate, they can precipitate out. It's almost like it'd be like a black. You could hit it with a hammer and it would shatter. Type typical asphaltene in production facilities. Now, why do asphaltenes precipitate out of an oil? Is typically because the pressure. Well, basically, if the pressure approaches the bubble point of the oil, typically asphaltenes will only be in oils, okay, where you have these really large molecules. Wax can precipitate from both oils and condensates and gases, but it's mainly oils. So asphaltenes will precipitate from oils. As the pressure approaches the bubble point and below, you'll have the maximum tendency to get asphaltenes, and also because of adding gas to the oil. So like if you have to lift the oil to the surface by injecting gas down in the tubing to lighten the column to get the oil to the surface, it's called gas lift. You're lifting the oil by injecting gas in the well. Gas lift can cause asphaltenes precipitating because it does. You can have gas mixing with the oil in a gas injection project, and when the gas coming through one formation mixes with the oil coming from another formation in the wellbore, that mixing causes asphaltenes in some cases to precipitate, and you start clogging the production tubing. And if you pull the tubing out and you start seeing this stuff, it's like black, hard material and stops the well from producing. Norway has very little asphaltene production, if any. I don't know if I've heard of any fields. You need more aromatic type oils typically to see asphaltene production. So that's a whole mixture of components, and it's very complicated stuff going on. But like I said, mainly it's a function of the pressure approaching the bubble point and basically the composition of the oil changing because of this adding the gas to some other composition. That other composition, for some reason, those asphaltenes want to drop out. Okay, so that's kind of a summary of the compositions. Like I told you before, you have molar compositions. Which we write Zi for this is the total mixture. So we've been talking about the total mixture in the reservoir. If we're just looking at a gas phase, and we know it's a gas, we use the term Yi. That's for a gas phase. Xi we use for an oil phase. And these are all summing to 1. They're mole fractions. When you sum over all of the components, is all summed to 1. And that's because we're simply taking the moles of the component I over the total moles in the entire mixture, just normalizing them. In the case of gas, it's the number of moles of I in the gas phase over the total moles altogether in the gas phase. And in the case of Xi, it's the number of moles I in the oil phase over the total moles in the oil phase. So it's just a normalization. That's what we call molar compositions. And you have the same, sometimes it's used and actually the lab measurements of composition are typically on a mass basis. So mass composition, you've got Wi is the mass of component I in the total mixture over the total mass. For the gas phase, we don't have a different symbol. We just say that that's the mole of component I in the gas phase over the total, mass. Gas. Shouldn't talk. The mass of component I in the oil phase over the total mass in the oil phase. So these are the symbols used for compositions. To go between mole fractions and mass fractions, to go back and forth, we need what everybody knows is the molecular weight of each component. Okay? So, molecular weight is defined as the mass of a given component over the moles of that component. So these are basically known values for our components. Our non-hydrocarbons are known, and our hydrocarbons up to about C5. But C6 is a mixture, okay? So we may or may not know the average molecular weight of that mixture very well. So we basically kind of know these are known values pretty much up to about C5, and then your reservoir, my reservoir, will have a different average molecular weight of C5. Maybe I'll say up to C4 then, something like that. So, but we know the molecular weights of isonormal C4 and isonormal C5, so I can say up to about C5. But then we basically, the molecular weights of for C6, C7 on up, there's more of an uncertainty. When I write plus minus, it means we don't know something exactly. Okay? And that uncertainty may be 1% to 10%. Like that very heavy C36 plus stuff, we don't know its molecular weight. Within 10% for sure. Okay, so it's okay. But if we have to choose a set of molecular weights for all the different components, we can then go back and forth between mole fractions and weight fractions or mass fractions using this definition here of molecular weight. Okay, so how would we do that? If we know mole fractions and we know weight fractions, how do you go back and forth if you know the molecular weights? Well, the average molecular weight is just the sum of all the masses over the sum of all the moles, right? The mole fraction would be this over this, and the weight fraction would be that over that, right? So we can combine these two and say that m over n, mass per mole, is equal to mi over, so we take m to the left, mi over wi, right? That's mass. That divided by n. N is ni over zi. So that's the same as zi over wi times mi over ni. All right? But this thing here is just the molecular weight of that component. Right? And this thing here zi over wi times mi. But this here is just the average molecular weight, right? So to go back and forth between wi and zi, would be m average over mi times wi, or written differently, zi So those are the ways you can go back and forth. So you basically need the average molecular weight, and you need the molecular weight of each species to go back and forth. Okay. Okay. I'm not going to go into the details of how the laboratory measures the compositions yet, but basically they're going to provide the WI values and the average molecular weight at a minimum. They'll give you that. Usually they give you the mass fractions, the mole fractions, and the average molecular weight. So the lab should provide at minimum. ZI, and average molecular weight. Often they'll provide all three of these. And they may actually give the molecular weights that they're assuming in the lab and this. What they actually measure is only weight fractions and average molecular weight, basically. Then they make some assumption on these. Okay, so that's okay. Any questions about this? Is all stuff you've had before, so it shouldn't be a problem. What's different now is that you basically have uncertainties in the reported composition because they don't know the molecular weights of all the species. Okay, and they have to make some estimates and guesstimates on that. So you don't really know the molar amounts exactly. Now, at this point, since we're going to try to give you an exercise. Now, in Chapter 2, there's a lot of stuff, so I recommend you try to read that. But in Chapter 2, the concept of phase behavior is covered in some detail. And in particular, the conditions of pressure and temperature for a given composition where you have single phase and where you have two phases. Okay? That's covered. And this map of pressure and temperature where you have one phase and two phase is called a phase diagram. It's a pressure temperature phase diagram. Okay, pressure temperature phase diagram. It's saying where do I have single phase, where do I have two phases, and it also indicates the single phase, whether it's oil or gas. Okay. You need to understand that to answer this problem that's going to be given here. How can this be that the lower reservoir, the deepest reservoir, is a reservoir gas, the mid reservoir is oil, and the shallowest reservoir is two-phase? How can that be? They all have the same composition. If they have the same composition, they have the same pressure, temperature, phase diagram. Okay? So let's look just briefly at the pressure, temperature, phase diagram for a few simple systems. Water. Okay? Water is a liquid or steam, right? Gas. Steam is gas. Okay? So that's our system. Water is the component. So Zi if we say H2O, that means Z H2O is how much? 1. Okay? So that's the system we're going to look at. Do you know any pressure, temperature, condition for water? Don't answer me out loud yet. I want you to write it down. Okay? Don't answer me out loud. I want everybody to try to answer it. Do you know any pressure, temperature, condition where H2O is both liquid and vapor? Just write it down. What condition, what pressure, temperature, condition where this system, H2O, is both liquid and vapor? Not oil, it's not oil. Liquid and vapor. Okay. This is random. I don't. Is Sebastian here? No. Not yet. Is Bo here? Okay. Bo? You have to speak loud. 100 degrees Fahrenheit? Huh? Speak up just a little louder. 100 degrees C. Okay, for meaning C stands for Celsius, I think, the guy. Yeah. 100 degrees Celsius, and what pressure? Standard pressure. 1 atmosphere. Yeah, 1 atmosphere. Which is how many bar? Do you know how many bar that is?
1 bar.
About 1 bar. 1.0135. But it's actually not that. But it's around 1 bar. Okay? So we know 1 point. It's gas. But is it gas or liquid? Gas and liquid. Okay, that means that at 1 atmosphere and 100 degrees C, you're going to see 2 phases. Is that correct? Okay. So now I'm going to go ask, let's see here, Nina?
I agree.
Okay, you agree. Now, do you have to see 2 phases?
Are you asking me?
Yes.
I'm guessing not, depending on the pressure.
Okay, the pressure's fixed. 1 atmosphere, 100 degrees C for water.
Yeah, I'm guessing since water starts to vaporize at 100.
Yeah.
We should see 2 phases.
You should see, at a minimum, you should see that first bubble. If you're boiling in the kettle, you're getting ready for class, you want tea, you got a sore throat. That first bubble, if you could look inside your tea kettle, when it hits 100 degrees C, you should see the first bubble. Okay? But in reality, that bubble might be there and you don't see it. So all you see is this vast liquid water, right? So that bubble can be infinitesimal in size. In reality, it can be just before the bubble appears. So in that case, you would say that it is only liquid. Okay? But it's at the verge of going 2-phase. Likewise, you could have steam, and that could be at 100 degrees C in 1 atmosphere. You don't see that first droplet of liquid condensing out. So you can say that it can be either fully vapor, just ready to condense out a liquid, or it can be fully liquid, just about ready to give a bubble of steam. Or it could be 50-50, 98, not 90-80. that would be an odd one. 90-10, 50-50, 80-20, okay? So it can be any combination from essentially epsilon to 1 minus epsilon of either phase. Okay. So that is 1 point. And if we draw the pressure temperature diagram for water, we've identified the 1 atmosphere point and the 100 degrees C here as a point on what's called the we're back to Sebastian. He's okay. Tobias? Yeah. What is this line called where we have conditions of two-phase for a single component? Remember? This is the vapor pressure curve. Okay, this is the vapor pressure curve. Okay? And this is for H2O, the way we've got it drawn. And along this line is the only line where you can have two phases of a pure compound, vapor and liquid. Okay? Is there another example that we have, not on a day-to-day basis, but come summer and the weather's nice and we want to go outside and grill a piece of salmon or a big steak or a hamburger, right? We usually use what's called, what do we use? You either use coal, charcoal, which is like heavy, these monster molecules, you don't want to know about those, or you use a cleaner fuel called natural gas, but it's actually, I think, propane, right? Propane. So it's essentially pure propane in this bottle. Has anybody grilled with propane? A little bit? Okay. Do you think there's one or two phases in the bottle? Two phases, okay. All the time, when you buy the bottle, it's two phases?
Maybe one phase, one light.
Maybe. Okay. I'm going to let you guys kind of carry that, think a little bit about that one with propane as an example, because it's an interesting example. But actually, when you buy the propane, I think it's actually two phases, but it's got a lot of liquid and just a little bit of gas. It's like the butane lighter, and there you can actually look at it, and you see when you buy it, it's not like they're cheating you. It's not filled all the way to the top. There's a little bit of, you see the liquid interface, right? That's because it's both gas and liquid in there. And I want you to think about what happens with the butane lighter or the propane tank as you use up the gas. Okay? What happens inside the container? So think about that till Tuesday. But that's another example of a pure compound on the pressure temperature